Welcome to the Explainer. Today, we're tackling one of the most common and, frankly, most annoying headaches in data science: missing data. You know, those little empty cells that can bring your entire analysis to a screeching halt? But don't you worry, we're going to turn that headache into a strategy.
So here's our game plan. We're going to follow a level-up structure for this. We'll start with the absolute basics, the quick fixes, and then we'll slowly build our way up to the most powerful and sophisticated techniques out there. By the end of this, you're going to have a full toolkit ready to go. And this is the critical question, isn't it? Because what you do next matters a lot. Simply ignoring or mishandling these gaps, well, it's not just lazy, it can completely break your models or, even worse, lead you to biased, fundamentally incorrect conclusions.
Okay, let's dive right in. Before we even think about fixing the problem, let's really get a handle on why it's such a big deal in the first place. Understanding the risks is absolutely the first step to choosing the right solution.
For starters, a lot of algorithms, right out of the box, will just throw an error if they see an empty cell. Now, the easiest reaction is to just delete the whole row, right? But if you do that, you're throwing away potentially valuable information from all the other columns in that row. And this is the core of the problem. You can't just ignore missing values. You need a deliberate strategy to save as much information as you can.
So let's get to our first level of techniques. These are the simple, fast, and often good enough methods that all fall under a category called univariate imputation. Think of these as your first line of defense. Think of it like this. It's a very localized fix. You're only looking at the one column that has the problem, not the bigger picture of the whole data set. It's kind of like fixing a pothole using only the asphalt from the street it's on.
So for columns with numbers, your two main choices are the mean and the median. The mean is just the good old average. The median, well, that's the value smack dab in the middle if you line them all up from smallest to biggest. The key difference, if your data has some really extreme values, we call them outliers, the mean can get pulled way off course, while the median just stays put. It's much more stable.
And you can see why these are so popular, right? They're incredibly fast and easy to do, but, and this is a big but, they have a major drawback. By filling all the gaps with the exact same number, you're artificially squishing the natural spread or variance of your data. Imagine a data set of house prices. If you fill in the blanks with the average price, you're making it seem like all the houses are more similarly priced than they really are. You're basically flattening the natural shape of your data. Okay, so what about stuff that isn't numbers? Like city names or product categories. You can't exactly calculate an average for those, so what do? Well, you find the most popular or most frequent value and just use that to fill in all the blanks. Simple enough?
But here is the catch, and this chart just shows the problem perfectly. Look at this. By filling all the missing values with the most common category, which here is TA, you can see its bar just shoots way up. You've now artificially inflated its importance and completely distorted the original distribution. You've actually changed the story your data is trying to tell. So all the simple fixes we've talked about try to hide the fact that data was missing. They try to sweep it under the rug. This next level of techniques, it does the exact opposite. It explicitly tells the model, hey, this data was missing, and treats that information as a feature in itself.
This is a really important conceptual leap we're making here. We're moving away from, let's pretend this value was never missing, to asking, what if the reason it's missing is actually useful information? Maybe people who didn't fill out a certain field all have something in common that our model can learn from. So for numerical columns, you can fill the gaps with some arbitrary number that's way outside the normal range, like 999 or -1. And for categorical columns, you just create a brand new category and call it, you guessed it, missing. Both of these methods create a really clear signal that the model can pick up on, which is especially powerful when you suspect the data isn't just missing randomly.
All right, we are leveling up again. So far, we've only been looking at columns one at a time, in isolation. Now, we're going to start using information from the entire dataset to make a much more intelligent guess.
This is where things get really powerful. We're now working under the assumption that the other features in our data can give us clues about the one that's missing. The idea is that the relationships between the columns actually matter, and we can use them to our advantage.
And the first and probably most intuitive way to do this is with the k-nearest neighbors imputer, or KNN. It's actually a beautifully simple idea. To figure out a missing value for one data point, you just go find a few other data points that are the most similar to it and see what their values are.
And this lays out the process perfectly. First, the algorithm zeroes in on the row with the missing value.
Then, it scans all the other columns to find the k most similar rows. Those are its neighbors. Finally, it just takes the average of those neighbors' values and uses that to fill the gap. See? It's a much more educated guess because it's using context.
And here we are. We've reached the final boss. This is an advanced technique that is so sophisticated, it basically turns your imputation task into its own full-blown machine learning problem.
This is MICE. It stands for Multivariate Imputation by Chained Equations. Yeah, I know it's a mouthful. You'll also see it called Iterative Imputer. But the name isn't what's important. The idea is that it works like a detective, building a case, using every piece of evidence to inform the very next step.
Okay, stay with me here, because this is a whole process. First, the algorithm makes a quick guess for all the missing values, maybe using the mean. Then, it picks one column and pretends its missing values are missing again. After that, it trains a machine learning model to predict those missing values using all the other columns as clues. Then, it updates the column with these new, smarter predictions. And it does this for every single column, one by one. But get this, the entire cycle of going through every single column repeats over and over again. With each pass, the predictions get a little bit better, a little more accurate, until the values finally stop changing.
So, wow. We've gone from a simple average all the way up to this complex, iterative machine learning model. With all these options on the table, how on earth do you choose the right one for your project?
Well, this right here pulls it all together. It's your practical guide. You can see the trade-offs. On one end, you've got your fast and simple methods like mean/median, but remember, they can distort your data. In the middle, you have signaling, which is a great strategic choice if you think the fact that data is missing is important. And then way over on the other end, you have the super accurate methods like KNN and MICE, but they come with a cost. They're slower and they take a lot more computing power.
And that is really what it all boils down to. There is no single best method that works for everything. The right choice always depends on your specific needs. Are you just doing a quick exploratory analysis where speed is the most important thing? Or are you building a high-stakes production model where every single ounce of accuracy matters? What your project demands? Well, that's what will determine your strategy.